Jai Hind students, myself Dr. Meenakshi from AKGEC Ghaziabad. Today I am taking one topic of Unit 4 for BTech first year students of Engineering Mathematics 1. Unit 4 is multiple integration, and I am taking one of the topic for this unit, which is change of variables. And in change of variables, I am taking how to change Cartesian coordinates to spherical polar coordinates. So why we need these changes? By using the topic of change of variables, the evaluation of double or triple integration is simplified by using the suitable change of variables. So the one means in many ways we can change Cartesian coordinates to either the polar coordinates or the spherical coordinates or the cylindrical coordinates. So I am taking here just one topic, means changing Cartesian coordinates to spherical polar coordinates. What the meaning? That I need to change the Cartesian coordinates x, y, z to the spherical polar coordinates, which are the coordinates r, theta and phi. So in spherical polar coordinates, we have x equal to r sine theta cos phi, y equal to r sine theta sine phi, and z equal to r cos theta. So that x square plus y square plus z square equal to r square. We can prove it by taking the value x square plus y square plus z square over here. Means if I take the square of this, I can write this is equal to, means r square is common out of each when I add them. So taking r square common outside, and inside I will get something like sine square theta cos square phi plus sine square theta sine square phi and plus cos square theta. And by using the trigonometric identities, what I can do, I can take the sine square theta common out here. So cos square phi plus sine square phi will be 1. And then sine square theta plus cos square, this theta. Cos square theta will be equal to 1, and giving you the value that x square plus y square plus z square equal to r square. So in this way, you change the Cartesian coordinates x, y, z into 3 new polar spherical coordinates, which are r, theta and phi. So now we look at when I change Cartesian to these type of spherical coordinates, what happened to the integral. So first of all, okay, for the integral I need the Jacobian also. What the meaning Jacobian? The Jacobian of x, y, z with respect to r, theta, phi. So you need to remember that you are converting the variables x, y, z into 3 new variables r, theta and phi. So you need to take the Jacobian of x, y, z with respect to r, theta, phi. You know the definition of Jacobian. This must be the determinant. This is not the metric. This is del x by del r, del x by del theta, del x by del phi in the first row, del phi by del r, del phi by del theta, and del phi by del phi in the second row, and del z by del r, del z by del theta, and del z by del phi in the third row. So when we solve this determinant, we know how to take their partial derivatives. So when we solve this determinant, we get the value equal to r square sine theta. You can all easily solve it by in the topic of Jacobian. And if the Jacobian is r square sine theta, then we know that when we start writing the integral, so I have the integral in Cartesian coordinates, which is triple integration, function of x, y, z into dx, dy, dz. So what we do, we need to convert it to the spherical coordinate. So in place of x, we replace the value r sine theta cos phi. In place of y, the value is r sine theta sine phi. And in place of z, the value is r cos theta. And what the value dx, dy, dz? Dx, dy, dz is replaced with the value mode of Jacobian into dr, d theta and d phi. So I need to find out the Jacobian, and Jacobian we have calculated in the last slide. The Jacobian for polar coordinates, we have to take its magnitude. So it's the value r square sine theta and dx, dy, dz converted to dr, d theta, d phi. So this is the final conversion of the given integral, which is given in the form of Cartesian coordinates in terms of spherical polar coordinates. So what means what we need to change? We need to change the function in terms of r theta phi, the value dx dy dz in terms of dr d theta d phi, and lastly we need the limits of r, theta and phi also. So on converting the limit, how we calculate the limits r, theta and phi? So look at the limits. Okay. For the whole volume of the sphere, spherical coordinates means obviously we are working for a sphere. So value limit for r moves from 0 to a, limits for theta is from 0 to pi, and limits for phi is from 0 to 2 pi. Means if I draw the circle, I know that this is the circle, this is the sphere in 3 dimension, and this is the sphere having center at origin and radius a. So r is nothing but the position vector, it's the limit ranges from 0 to a. What is this phi? First we talk about this phi. Phi is the angle of rotation of the sphere on its axis. So just like the earth moves on its axis, the total angle of rotation is always equal to 2 pi. So for the whole sphere, whole volume of the sphere, the angle phi takes the value from 0 to 2 pi. And what is this phi? Phi is the angle of rotation, means if this is your sphere and you need to rotate it like this one. So this angle is nothing but the angle phi. So phi takes the value only from 0 to pi. So the value for phi is 0 to pi, theta is 0 to phi, and phi value ranges from 0 to 2 pi. This we have discussed for the whole volume of the sphere, means if you are taking the full sphere. What happened next? For the part of the sphere, x square plus y square plus z square equal to a square in the positive octant. You know that any of the 3-dimensional shape, we can divide the 3-dimensional coordinates into 8 number of octants. So we are taking here only the part of the sphere in the positive octant. So what happened in the positive octant? The limit for r remains same from 0 to 2a. The limit for theta now will become changes only from 0 to pi by 2. Means you are taking only the half of the part of the portion which lies in the positive octant. So theta only take this much value, means 0 to pi by 2. And phi also for the positive octant take the value from 0 to pi by 2. So means you need to remember that for the positive octant, theta and phi both take the value limits only from 0 to pi by 2. Look at the C part. For the part of the sphere, this above xy plane. Here I am taking above xy plane. What's the meaning above xy plane? If you look at this figure, above xy plane means you are taking only this portion of the sphere. Means here you have only the hemisphere. Hemisphere means the half of the sphere. So when you are dealing with the hemisphere, limit for r remains same from 0 to a. Limit for theta for the hemisphere also moves only from 0 to pi by 2. But what about phi? Means if you are taking only this hemisphere also, and if I say that you need to find out the angle of rotation, this also moves on its axis from the limit 0 to 2 pi. So the limit for phi here also remain the same from 0 to 2 pi. So they are the 3 limits. Means if you remember that for the whole volume, theta takes the value 0 to pi, phi takes the value 0 to 2 pi. For the positive octant, theta also take the value 0 to pi by 2 and phi also take the value 0 to pi by 2. And for the part of the sphere above the xy plane, theta takes the value 0 to pi by 2, but phi takes the full value, means 0 to 2 pi. So if you know that these are the, means either you have given the whole sphere, or you have given the part of the sphere in the positive octant, or you are given the part of the sphere above the xy plane. So these limits are fixed. You need to remember these limits, that they are the limits when you are converting the Cartesian to spherical coordinates. Okay. So now look at one of the example. The first example I have taken to find out the volume of this sphere. Find out the volume of the sphere x square plus y square plus z square equal to a square by changing into spherical polar coordinates. So it's mentioned over here that I need to convert these x, y, z Cartesian coordinates to the spherical coordinates. I need to find out the volume of the sphere. So we know that the volume of the sphere is given by triple integral dx, dy, dz. This is the formula to calculate volume. Triple integration dx, dy, dz. I need to convert it to spherical coordinates. So I know that in spherical coordinates, we have just discussed that x I can write r sine theta cos phi. Y is equal to r sine theta sine phi. and z equal to r cos theta. They are the spherical coordinates. And when you convert to the spherical coordinate, so we know the Jacobian means the value dx, dy and dz. This converts to mode of Jacobian dr, d theta, d phi. And when we convert to spherical coordinates, we know that there's nothing but r square sine theta into dr, d theta, d phi. So means we get the values of x, y, z also, and we get the value dx, dy, dz also. So now we know that here none of the function is here. We just need to find out the volume of this sphere. We put the value of dx, dy, dz. Dx, dy, dz is nothing but r square sine theta dr, d theta, d phi. Next I need the limits for r, theta, phi. So what we have taken? We have taken the volume of the full sphere here. We are not taking any of the part of this. So we know that for the whole sphere, what the limit for r? The radius of the circle is a. So r varies from the limit 0 to a. For the full sphere, I know that the limit of theta is from 0 to pi. And for the limit of phi will be of 0 to 2 pi. So if you remember the limits that for the whole volume theta varies from 0 to pi, phi varies from 0 to 2 pi, then there is no need to think over here. Just put the limits over here. Now I just need to evaluate it. First I integrate with respect to r. So taking the integration with respect to r, the integration of r square will become r cube by 3. And when we put the limit, so this will give you the value a cube by 3. So I can put it directly. I can writing this a cube by 3. The limit for phi is 0 to 2 pi. The limit for theta is 0 to pi. And the function I left with is the sine theta into d theta into d phi. Because we have just evaluated with respect to r over here and put the limits. Now I'm integrating with respect to theta over here. So I know that the integration of sine theta is nothing but minus cos theta. So put the value, this is a cube upon 3 from the limit 0 to 2 pi. Integrating sine theta, this will become minus cos theta from the limit 0 to 2 pi. Put the limits. So this is nothing but a cube upon 3, 0 to 2 pi, minus of cos 2 pi. I can take this minus common outside, minus the lower limit cos 0. Cos 2 pi is 1 and cos 0 is also 1. Means I'm taking the minus common outside, cos 2 pi minus the lower limit cos 0. So cos 2 pi, you know that is the value 1 and cos 0 is also 1. 1 minus 1. Okay, this is minus and this is, we'll take the value plus. If I take the minus sign common outside, this is cos 2 pi minus cos 0. So this will give you the value plus 2. And 2 I will take common out here. This is the value 2a cube by 3. And there is no function of phi over here. So we just put the limit phi over here, giving you the value 2 pi multiplied over here. So what we'll get the answer? We get the answer 4 pi a cube upon 3. This will become the volume of the whole square. 4 by 3 pi a cube will be the volume of this sphere along the first quadrant. Okay. So this is how we convert the Cartesian coordinate to spherical coordinates and we try to solve it. So coming to one more example, look at. Example says evaluate triple integration x, y, z dx, dy, dz over the positive octant. Here it's given the positive octant of the sphere x square plus y square plus z square equal to 1 by changing into spherical polar coordinates. Means here you are taking only the part of the sphere which is lying in the positive octant. We need to find out this evaluation. So first of all, we start taking the spherical coordinates. We know that in spherical coordinates, we have just discussed that we put x equal to r sine theta cos phi, y is equal to r sine theta sine phi. And z is equal to r cos theta. we need to put this value. And we know on taking the Jacobian, the value dx, dy, dz is nothing but r square sine theta, dr, d theta, and d phi is the value. Yeah. And for the positive octant, also we have discussed that r take the limits from 0 to 1. 1 is the radius of this sphere. Theta takes the limit from 0 to pi by 2. And phi also take the limits from 0 to pi by 2. This we have already discussed. So now we know the limits. We know the values of x, y, z as a function of r, theta, phi. We know the values of dx, dy, dz in terms of r, theta, and phi. So now we substitute all these values in this integral and try to convert this integral to spherical polar coordinates. So we look at the next slide. We have triple integration x, y, z, dx, dy, dz. Okay. So we now start evaluating this triple integration x, y, z into dx, dy, dz. Just make all the substitutions. So we have triple integration. X is nothing but r sine theta cos phi. The value y is r sine theta sine phi. And the value z is r cos theta. R cos theta. And the value dx, dy, dz I am writing over here r square sine theta. This is dr, d theta, d phi. And now we put the limits also in the next step. So first what we do, we combine all the, I can put the limits also. The limit for r we have taken from 0 to 1. The limit for theta is 0 to pi by 2. And the limit for phi also is 0 to pi by 2. We can put the limits. Okay. So now we just need to combine all the coefficients of r here, sine theta and cosine theta. So I can write this is nothing but 0 to pi by 2 integral 0 to pi by 2. If we look at the total power of r here, it's r into r into r into r square. So this will become r to the power 5. So I can write this is r to the power 5. Look at the sine theta. It's sine theta into sine theta is sine square theta into sine theta will become sine cube theta. I can write this is sine cube theta. Next is value cos theta. Cos theta is appearing only once. So I write here it's cos theta into. Now coming to the phi functions. One is sine phi and one is cos phi. So I write over here one is sine phi and one is cos phi into dr, d theta, d phi. Yeah. So we have covered all the values for r, theta and phi over here. First we start integrating. Okay, once I put the limit for r also, it's 0 to 1. Okay. Now I start integrating with respect to r first. The integration of r to the power 5, you all know it's r to the power 6 by 6. And when I put the limit 0 to 1, so it's nothing but equal to 1 by 6. So I'm directly taking that 1 by 6 common outside. And now I'm writing this integral as the product of two integrals. One integral I make for the functions of theta. And one integral I make for the functions of phi. And since both the limits are 0 to pi by 2, 0 to pi by 2, so you can keep it like this. I can write the first integral I am making for the functions of theta over here. What are the theta functions? It's sine cube theta. And the second function is cos theta into d theta. This one. And the next integral I am writing for the functions of phi. It's 0 to pi by 2. We have sine phi and cos phi into d phi. Sine phi, cos phi into d phi. So now I just need to solve these two integrals, one as a function of theta and one as a function of phi. And now you have so many ways to solve these integrals. Either you use your classical method, means you start putting sine theta equal to t and writing cos theta d theta equal to dt and change the limits also as a function of t. Or you can also solve it by using the beta and gamma functions. You know that in beta and gamma functions, you have a formula. You know that it's the formula is that integral 0 to pi by 2, sine to the power m theta, cos to the power n theta, d theta. You can evaluate this type of integral by converting it to gamma functions. So, but I am here taking the traditional method, means I am in this integral. To evaluate this integral, I put sine theta equal to t. If I differentiate it, I get that cos theta d theta will become equal to dt. Means this cos theta d theta will become dt, and sine theta, in place of sine theta, I can put it equal to t. Look at the change in limits. At the lower limit, 0. I know that sine 0 is 0, so t take the value 0. And at upper limit, pi by 2, you know that sine of pi by 2 is nothing but equal to 1. So, converting this integral into the sine integral in t, I can write this 1 by 6. Limit will become 0 to 1. In place of sine theta, we will put the value t. This will become t cube. And cos theta d theta will be written as the value dt. Okay. Similar, to solve this integral, let I put sine phi equal to some value u. This one. And I get that cos phi d phi will become equal to du. Again the same, when I put the limit 0, sine 0 is nothing but 0, so the lower limit for u will become 0. And when we put pi by 2, sine pi by 2 is nothing but 1. So the upper limit for u will become equal to 1. So converting this integral in terms of u, I can write this is nothing but again 0 to 1. This is u, and cos phi d phi will become equal to du. And they are very easy integrals now to evaluate. I can write this nothing but 1 by 6. This will become t to the power 4 by 4 for the limit 0 to 1 into u square by 2 from the limit 0 to 1. Just put the limits. So it 1 by 6 into here for the upper limit the value is 1 by 4, and here for the upper limit the value is 1 by 2. Giving you the value 6 4s are 24, 2s are 48. So the answer for this integral in the positive octant will become equal to 1 upon 48. This one. Okay. We write it over here. The answer for this integral coming out to be equal to 1 upon 48. This answer. Okay. So you think that, you know that how we going to convert, means if I need to convert this integral in terms of Cartesian coordinates, so it's very difficult to evaluate it, because then the limits are very tough for the positive octant. So it's very easily converted to spherical coordinates. And in spherical coordinates for the positive octant, we put the limits over here. Just we converted it in this form. Write it as the product of two integrals. Putting the sine theta value equal to t and converting it to the integrals of t and u. We just find out the answer that the value is coming out to be 1 upon 48. Yeah. So means the change of variables converts your given integral into a simpler form by putting the limits, because all the three limits coming out over here are constant limits, like this one. Okay. So you can look at one more example, this one. What the question? Question says evaluate triple integration x y z x square plus y square plus z square to the power n by 2 dx dy dz over the positive octant. Here also you are provided the positive octant of the sphere x square plus y square plus z square equal to b square, provided n plus 5 is greater than 0. Means here it's not mentioned that you have to convert this to spherical coordinates. But you know that for this sphere, if you try to solve this integration in Cartesian coordinates, so it's not easy to evaluate it. So what we do? We're going to convert this again to spherical polar coordinates. Yeah. So when we start the solution, I'm writing again that I know that x is r sine theta cos phi, y we put for r sine theta sine phi, and z is equal to r cos theta. Sorry, this is y, and z is equal to r cos theta. And also we know that I'm writing dx dy dz is nothing but the mode of Jacobian dr d theta d phi, which is nothing but the r square sine theta. So I'm putting these values directly over here and try to convert this integral to spherical coordinates. Look at what we get. So I'm writing now this integral. I'm writing the triple integration. First I need the product of x, y, z. So just do the product of these three. It's r Just like the previous question, sine theta cos phi. And this one is r sine theta sine phi. And this is r cos theta. What next? Next is the value x square plus y square plus z square. And we know that when we are converting x, y, z to Cartesian spherical coordinates, then in the first slide we have discussed that what is the value of x square plus y square plus z square. It's nothing but equal to r square. So putting the value x square plus y square plus z square equal to r square over here, nothing but r square to the power n by 2. And dx, dy, dz is replaced with r square sine theta dr d theta d phi. Dr d theta d phi. Okay. So finally, I know the limits also in the positive octane. The limit for r for this sphere of radius b is 0 to b. For the limit theta, it's again 0 to pi by 2. And for phi also, this is also equal to 0 to pi by 2. Is the value. So now just the same thing, we need to combine the various parts of r over here. Look at, here this 2 will cancel out. So it's r square, r cube, r to the power 5. And here it's r to the power n. So total power of r will look at the value of r to the power n plus 5. So if I integrate this r to the power n plus 5 with respect to r first, so what I get? I get 0 to pi by 2, 0 to pi by 2. The integration of this will become r to the power n plus 5 upon n plus 5 from the limits 0 to b. And I can combine the other trigonometric functions also. Means sine and sine gives me the value sine cube theta and single cos theta and cos phi and sine phi. Sine phi, cos phi and the value d theta and d phi. The same as the previous question. Putting the limit of r here, I can take this b to the power n plus 5 common outside divided by n plus 5. This one. And what else I left with? I left with the 0 to pi by 2. One integral I am making for the sine function means sine cube theta, cos theta, d theta. And one integral I am making for the cosine phi function, the sine phi, cos phi and d phi. Sine phi, cos phi and d phi. Fine. Okay. So now just, this is constant. This is the same integral which we have evaluated in the last slide. Okay. But now, we try to solve it by using the beta gamma functions also. Okay. So what we do in the next slide, I am writing this equation again. Means it's, I am writing like this one. It's b to the power n plus 5 upon 5, n plus 5. We have 0 to pi by 2, sine cube theta, cos theta, d theta, and in the second integral we have 0 to pi by 2, sine phi, cos phi, d phi. So let some of you think of solving it by using the beta and gamma functions. So we know that in beta gamma functions, integral 0 to pi by 2, sine to the power m theta, cos to the power n theta, d theta. This is nothing but gamma m plus 1 by 2, gamma n plus 1 by 2 upon twice gamma m plus n plus 2 upon 2. That's the value. Okay. So I use now this formula to evaluate this integral. Coming to the first integral. M here is equal to 3 and n is equal to 1 here. So apply this formula and this will become b to the power n plus 5 upon n plus 5. What I can say, this is gamma. M here is 3. So it's 3 plus 1 by 2 means 4 by 2 means it's gamma 2. N here is 1. 1 plus 1 by 2 means gamma 2 by 2 means gamma 1. Upon twice gamma. M plus n plus 2 by 2. M here is 3 and n here is 1. So this will become 3 plus 1 plus 2 by 2. Means gamma 6 by 2. Means this is nothing but equal to gamma 3. This is the value of the first integral. Similarly, I can solve the second integral. Here m is also equal to 1 and n is also equal to 1. Just put the value. When I put m equal to 1, it will become 1 plus 1 by 2 means gamma 1. Similarly, the gamma 1 by 2. What will become this? It will become 1 plus 1 plus 2 by 2. Means it's the 4 by 2 means nothing but equal to gamma 2. So now I can easily solve it. It n to the power 5 upon n to the n plus 5. Gamma 2 is nothing but 1 factorial, which is 1. Gamma 1 is always 1. And what is gamma 3? Gamma 3 I can write equal to 2 factorial. Coming to second one, both of the numerator value giving you the 1. Gamma 2 is 1 factorial. I left with the value 1 by 2. So nothing but 2 2s are 4, 2s are 8. So I get the value b to the power n plus 5 upon 8 into n plus 5. This is the value in this integral. So means these type of integrals in the limit 0 to pi by 2 we can also evaluate by using the beta gamma functions. So I have so many ways to evaluate these type of integrals, either by using the classical methods or by using the beta gamma function. So you have seen in the slide that in this video that converting Cartesian coordinates to spherical coordinates, you can make your integral easily solved, and you can solve it easily by putting the constant limits for the just along the volume of the full sphere. Thank you.